Now, as we already know what is parallax, we can use this method. Parallax is nothing but difference or change in position of the object with respect to background when seen from two different positions. So now we can use the parallax method to find out what is the position of a distant object or the objects which are very far away from the surface of Earth. For example, a star or maybe another planet, like that. So for example, let us consider that this point O is a moon, for example. Okay, so point O is what? Point O is basically a moon, or we can consider it as a pencil, what we have seen in our example. So O is nothing but a pencil which is in front of our eye, or we can consider it as a moon which is away from the surface of Earth. So when we looked at moon from one point on the Earth, so let's say this point P is a point on the Earth surface. From there we are looking at a moon which is at very far distance from us, and capital D, we assume that it is the distance between the position of moon and our point on the surface of Earth. And then we looked at the moon again from a second point or different point, which is point Q, from on the surface of Earth, and then we noted and assuming that capital D is the distance between the point between the position of a moon and our position on the surface of Earth. Remember that this point P is on one corner of the Earth's surface, or one edge. For example, if we consider Earth, Earth has two opposite poles. So for example, the upper pole, we call it as a north pole. So we took the reading of moon, or we looked at moon from the north pole, or point P, and then we went to the opposite end, okay, at point Q, which is at the south pole. So first we looked at the moon from north pole, which is at point P, and then we looked at moon from the south pole, which is at point Q. So these 2 points, they are known as diametrically opposite. Okay, if we join the two poles of Earth using a straight line, so point P will be on one end and point Q will be on another end of the Earth's surface. So because we already know what is the diameter of the Earth, the distance between point P and Q will be known to us. Fine. So this distance between point P and Q, the diametrically opposite point, is known as basis. Okay, and because we already know what is the diameter of the Earth, we know the distance between point P and point Q. Also, using some instrument and instruments, we technology we use, we find out what is the angle between this distance between these two observation lines. So this is first observation line and this is second observation line. The angle between these two observation line is known as parallax angle. Fine. So this is, or sometimes we also refer it as paralytic angle. So I hope this is clear. Point P and Q are the opposite ends or diametrically opposite ends of the Earth's surface. Now because we are looking at the moon from the opposite two ends, now we know what is the basis, and somehow using instrument we also calculated what is the angle between these two observation, which is known as parallax angle. Now consider, now assume that this point O is somehow extended backwards. So like a rubber band, if we hold this O and we push it backward, what will happen? The capital D, the distance capital D is going to increase and B will remain the same, because capital D is going to increase, so theta should, basically the parallax angle should decrease. If we stretch this point O, the angle will become smaller. Fine. So now if we assume the object is very far away, the moon is not at this position, it is even backwards. So what will happen? D is going to increase and B will be same. Now whenever in mathematics you would have studied, whenever the denominator is bigger than the numerator, okay, so here numerator is basis b and denominator is capital D. So denominator is bigger, then the total value is less than 1, okay, 0 point something something. So b by d is very very small, remember that. And then this is the most important assumption over here. Whenever we measure larger distances, always d is bigger than the b, so the value is less than 1, very very less than 1 actually, okay. And also we found out that theta is going to decrease, okay, because we are pulling this point o backwards, the value of theta should decrease. So if we assume this as a part of our sector, in mathematics we study sector. So this is one piece of a circle, this will be a curved portion, right? And because we are pulling this point O, so the angle becomes very very small, and therefore this curved line will be same as a straight line, it will become a straight line, okay. We can take an example. We know that earth is a spherical surface, it is a curved body, but because we are standing on the surface of earth, very close to earth, standing exactly on earth, so what happens, the ground appears to us as a flat surface. So similarly, when the theta decreases, the curved portion that appears, when if we look at earth from distant place, it will appear outside the earth, so then it will appear a curved surface. But if the angle decreases or we are standing exactly on earth's surface, it appears to us as a straight line. So now the curved portion will appear to us as straight line, and b, distance b will be same as s when theta is very very small, very importantly. Fine. So now we know how to find out the length of the arc. The formula for length of the arc is arc length s is equals to the radii, the radius from the center of a circle, and then into theta. So this is how we write down, this is how we write it down. So s is the arc length, r is the radius of the sector, and theta is the angle between the two radii. Fine. Now because in our case s becomes b, so we can put a b in place of s. R is nothing but capital D, and theta is as it is parallaxic angle. Fine. Angle PO and Q, we can call it as a theta. So after substitution we end up getting this, and because we are interested in parallaxic angle, so we get it like this. So parallaxic angle theta is equals to basis divided by the distance or length of the observation lines. So this is what is called parallax method, using the phenomena of parallax, or the observational difference from the left eye and right eye. We are able to measure by comparing the two observations, we are able to measure what is the angle theta. And now because if we know b and d, see there are many ways to look at this expression. If we know basis, if we know parallaxic angle, if we know b and theta, we can calculate capital D. If we know d and theta, we can calculate small b. Okay, so it is very easy now to find out the what is the size or diameter of an object which is far far away from us. Okay, for better understanding, we'll solve one problem from the textbook. Actually, the problem says a moon is observed from two diametrically opposite points, capital A and capital B, on earth. So if we are standing on earth's surface, one value we measured or we read or we noted from the north pole, which is north pole of the earth, where we have point A, and then second point we noted from the south pole, where we are taking as point B. So we know the basis, which is given here. A diameter of earth is approximately 1.267 into 10 to power 7 meters. Okay, so this is the diameter of the earth, basis. Fine. The angle theta subtended, so if we know small b, then only two values are left, one is capital D and another is theta. Somehow the question says the angle theta subtended at the moon on the two directions of observation is 1 degree 54 minutes. So we already know the theta value. Then what is left? Only thing left is capital D, which we can compute with the help of parallax method. So what is compute the distance between moon from the earth? So capital D. We are interested in looking capital D, like we can see here. The distance between the moon and any point on the earth is nothing but capital D. So using parallax method, we are going to solve it. So we know there are always steps to follow. So first step is nothing but given. What is given to us? It is given that the angle subtended or the parallatic angle between two observation points or observation line is 1 degree 54 minutes. So first we have to convert everything in radians. So how do we convert this 1 degree 54 minutes to radians? So first of all, we know that 1 degree is equals to 60 minutes. Okay, so because 1 degree is equals to 60 minutes, okay, and if we add 54 to it, the total will become 114 minutes. Okay, so first convert degree into minutes. This is how we do this. 114 minutes. Now we know that we know the value of 1 minute. Okay, we have seen already, so we can multiply the value of 1 minute to 114 and it will become 114 minutes, which is, so value of 1 minute is 4.85 into 10 to power minus 6 radians. Okay, and the answer comes out to be as 3.32 into 10 to power minus 2 radians. So first we obtained everything, the angle in radians, and we already know what is the diameter of the earth's surface. So using and we are supposed to find what is the distance between the sun and the earth. Now we know from the parallax method, the formula for parallatic angle is what? Theta is equals to b by capital D, and then we rearrange it to obtain capital D. Okay, first step, always get the right formula. Second step, put the values or substitution, and third step will be, or the process, or fourth step will be getting the answer. So this is how we use parallatic method to find the distance between the moon and the earth. So the distance between moon and the earth is 3.84 into 10 to power 8 meters.